Swayam Prabha. Digital India. Educated India.
Yeah, let's start. So we started discussing about Markov processes in the last class. So Markov process we also called as Markov chains, and we are mostly interested in discrete time Markov chains. So in the last class we defined what we mean by this Markov property, and then discuss what we mean by time homogeneous Markov property, and then try to connect transition probability matrix with my n step transition probability matrix, right. So in the last class we said that P of n is equals to P to the power n, right. What was P superscript n means? This is the n step transition probability matrix, and what is P here? One step transition probability matrix, or we simply call it as transition probability matrix, right. And we have also concluded that P of 0 is 1, sorry, I, identity matrix. Okay. So in the last class we just shown that P n plus m can be written as P of n plus into this product, and at the end we said that we could write it as P of 1 and P of n minus 1, and then we said that so P of n we are able to split it in this fashion, and we could further split them into this fashion, and we said that this can be finally result in P to the power n. Okay, fine. Now because of this, so I think Bested last time, after completing this, I also wanted to introduce the notion of finite dimensional distributions, which I couldn't do last time. Let me finish this today before moving to another topic on this Markov chains. We told that any process, a stochastic process, to completely characterize this, I need to give as finite dimensional distributions, right. That is, I need to, for any n, if it is a discrete time process, I need to characterize joint distributions or joint probabilities of this format, assuming that I am looking into random variables that are discrete, that is, let us say let me write it as m. So this is a joint distributions involving n random variables, involving n random variables here, and I need to give such joint distribution for all possible collections of my random variable to completely characterize my random process. So here I have taken some particular m random variables at time index n1, n2 and nm. You can choose any time index you want, okay. and this could be again for all time indices. You take any number m and take any time indices m, and let us say I have such a distribution, how we need to characterize this. I should be able to do, then that will give me complete characterization of my random process. And just J1, J2 are the possible realization this random variable can give. So I need to also define this for all possible values my random variables can take. Now let us see if this, what are the things that govern this finite dimensional distribution in the case of a Markov chain. Okay. I have this, what I could do is I am going to just introduce this initial state and then keep everything. So if I do this, nothing changes, right? These two quantities are the same, like I have just introduced this x0 random variable and just summed it over all possible values it can take. We have said that all possible values are coming from this state space S. Now you can split this probability what I call a J1 given x naught equals to I naught. Okay, and further you can keep on doing this. Right. Here it is x and 1, right. So I just first brought this out and then conditioned upon on that, then I brought x1 1 out, and then in the second time I just conditioned this random variable on that. Now you can keep on doing this. Now let us try to understand this part. So what is this? Now what I am asking, you are in the beginning in the 0th round, I am in state I naught, and then I am going to jump to state J1 in n1 rounds. This is, you are basically jumping in n states from state I0 to J1. What is this probability in our notation? P I naught J1, and what is the superscript? So it is going to be basically n1 minus 0, right, like the number of steps is n1, I will just write it. Now if you look into this, does this probability here depends on x naught equals to I0? No, right, because if once I condition it on something beyond I0, that is x and 1, this guy does not depend on this. So I could just write it as I can further split it like this. right. Now what is this quantity here? This quantity I know that it does not depend on x0 equals to I naught. So in that case what is this probability then? So is it okay, is it correct in our notation if I write it as, so this is J1 here, right, not I1, J1, and this is going from J1 to J2 in how many steps? N2 minus N1, right, and I can keep on repeating these steps, and finally what last step I am going to get is Jm minus 1 times Jm, and what is this guy going to be? Right. Now let us focus on the last term. So whatever this joint distribution of m random variables, I am able to now express in terms of this. Now each of the terms here, p I0 I1, so superscript n1, this is a n1 step transition probability matrix, right, and similarly this is n minus 2 n1 length step transition probability matrix. So all of this quantity here, they depend on transition probability matrix of different steps, okay. But what we have demonstrated earlier is whatever is the step you are looking at, all that can be obtained by one single transition probability matrix by appropriately exponenting it, right. So now all these quantities, my claim is they can be computed from my transition probability matrix P, is that correct? Right, but for the, so this quantity how can I write? I can write it as p raised to the power n1, but which term? This is the matrix, right, p raised to the power nm, if p is the transition, in that which term I will be interested in? I0 J1, this is a matrix, right, I have to tell both row and column indices. So all these things can be obtained from transition probability matrix P. So fine, all these things could be obtained from transition probability matrix P, but still to complete this finite dimensional distribution, I need one more term, which is, what is the probability that x naught equals to I naught, and this is usually called the initial distribution. So x naught, right, that is your initial step, and you want to know what is this probability that my initial step takes state I naught, and you want to know it for all possible states. So this is called I naught, where your I naught belongs to S is your initial distribution. Or initial probability distribution. So, and often this is denoted as pi. So if you know this initial transition probability matrix and your transition probability matrix P, do you think you will be able to characterize all finite dimensional distribution of a Markov chain, right? So now this contrast this with IID process. When you have IID process, to completely define my IID process, what I needed to tell you, just one distribution, right, that one distribution that is common across all the random variables. But now here, to completely describe a Markov chain, I need to tell you two things. to completely describe a time homogeneous Markov chain, and it will tell you its initial distribution and its transition probability matrix. So as you see, like the initial distribution is important, because where the Markov chain goes after some round depends on where, at which point it started. If it starts at different point, maybe the future I am going to see may be different. So that is why to completely describe a Markov chain, I have to tell you the initial distribution as well as my transition probability matrix. So initial distribution tell you, okay, where you are starting, and transition probability matrix will describe how you are going to evolve from that point. Okay, so Markov chains, the way we have describes it, they capture actually a lot of things that happen that we face in reality, and they give an often nice characterization of those phenomena. For example, let us say you want to model some let us say aircraft. So we want to model or you want to analyze where it is going to go and how it is going to go. Suppose let us say its trajectory is mostly defined by what? Its velocity, its acceleration, let us say, and maybe it also depends on how much fuel it is carrying. So once you give it some initial trajectory and you want to start looking at its position at different times, let us say you are going to look at its position at every second, or let us say every minute. Now whatever it reach, let us say at certain point of time, let us say at every time I am going to measure velocity, its acceleration at that time, and also the fuel, amount of fuel it is carrying that time. If you know that, based on that itself you could further analyze further how far it is going to go, right. I do not need to know what all the values of the acceleration and the velocity or the fuel it carried in the previous time instances. If let us say if I measured it at, let us say t equals to 100 unit, then that is enough, like all the things that has happened before it is kind of captured there, right. Yeah, fuel has been consumed till this point, but what remains is of importance to me to know the future. So in essence, the current time is kind of already capturing the summary of what has happened in the past. So if you tell me past entire thing, I can tell you what is the current thing, but if I tell you what is the current status, yes, it is a kind of summary of what has happened. It may not tell you what all happened, how the things happened in the past, but it contains the summary of the things that have happened so far. That is enough for you to describe future. For example, if you just know at time t what is the fuel remaining and its current acceleration and all, that is enough for you to see how my aircraft is, how far it is going in the future, right. So Markov chains are exactly doing this. They are just saying that if in your scenario is such that the current state is capturing enough information or kind of summarizing what has happened in the past, then you can ignore the past, and your future will be just you can analyze your future based on this current information. Initial x naught.
Why it is depending on the x naught? It should depend upon the latest information available, that x and 1.
Right, but I am, of course it depends, x and 1 depends on what happened in the x n1 minus 1, the previous lot, but here I am just trying to characterize the distribution jointly at different time instance.
Yeah, so it should depend upon the, just depend upon the starting point. Why the origin?
But the origin I am not interested in, right. I am just interested in calculating the joint behavior at this point. Indeed, what is happening, going to happen here, will depend on what is going to, from where you are going to start. So that is why this behavior is going to affect what is we are going to see at N1. We are just trying to capture that summary, not like what is happening in between. Even when you are going to look at finite dimensional distributions, right, even you need to characterize that aspect also. So for example, here N1 could be just 1. I am considering all possibilities of the indices, right. I am not ignoring that fact. So for example, here N2 could be just N1 plus 1. Not only one step how it is going to affect all, and I am also going to look at jointly all the distributions. What you are asking in this? You are asking to find all these joint distributions, right. You are not asking it just like how it depends on the previous one. What we are trying to describe here is, when we have a Markov chain property, when you have Markov property, all these joint distributions are going to be just captured by my transition probability matrix and my initial distribution. This transition probability matrix is already trying to capture all you are asking it for. From this state, what is the probability that I go to next state? But that is not the only thing I will be interested in, right. Maybe like to completely understand the process, I need to know all these joint distributions. For this we are saying, if you want to just, what you are asking is, okay, N1 will only depend on what has happened in the previous step, that is fine, because I am saying that it do depend on where you are going to start from. If you are going to just, okay, you only going to give me from N1 minus 1 and you are asking me, okay, what is going to happen, but that is not going to completely describe my process, right. I may be interested even to know what was before that. That is what the meaning of FDD is. All possible description I need to give about the process. We are just trying to model this. Yeah, okay, somebody has given you, and then I want to analyze the system. How to obtain this transition probability matrix is a different question. For that one has to, really do big experimental setup, do real measurements. So in this course, like right now we are putting all these things under carpet. Okay, how we are going to compute this initial probabilities, how we are going to obtain this transition probability matrix. This is all, there is a separate thing of how you are going to find this, like you have to do simulation and then try to estimate this parameter. So these are all parameters for us. P is a transition probability, means it is a parameter, it is a matrix with so many parameters. I do not know those parameters. What I am just saying that, see, if you pass on these parameters to me, I am going to analyze and tell this is how your system is going to behave. Okay, and so for example, that is how, right, like if you want to evaluate 2-3 aircrafts, each aircraft will come with its own parameters. Then as a system analyst, you will sit, okay, take all these inputs and then you try to analyze the system. And who is going to give the parameter for this system? Say like the vendor will give you the system. He would have said, okay, these are all my system. So it is fuel efficiency is this, it can sustain this much of turbulence, and it can go at this speed, and this, it can take this much acceleration and all. Using those things, you will come up with this set of parameters and then use it to understand your future. Okay, let us understand another example. All of us know queues, right, like we wait lot of time in the queues. So let us say we have a queue and there is a server. Let us take a simple idealized case where time is slotted, like at every time a guy may come and join the queue. So in every slot there is with some probability a new guy will come and join the queue. It may happen that in that particular slot nobody will join, but with some positive probability he may also join. Now and also meanwhile there is a server here which keeps serving you. Let us say you are just in a going to watch a movie and you are in the line to get the ticket. So somebody is preparing a ticket for you, and as you get the ticket you will move out, and lines may either grow longer or grow shorter depending on people are joining or people are exiting the system. Now let us say at some point, let us say at time xn, so n is going to tell you how many people are there in the queue at time slot n. So how you are going to define time slot is up to you. You may want to count the number of people in the system at, let us say, every second or maybe at every minute. It depends on the it depends on the scenario. Like if people are coming very frequently, you may want to take a smaller time scale. If your people are coming slowly, you may want to take a larger time scale. So time being, let us say this is just n equals to second, n second 1, second 2, like that. Every second a guy will join the system with some probability, and you want to see how many people are there in the system. Okay. Now so time being, assume that you know this service rate, the way this guy is preparing the tickets, then by that you can kind of understand at what rate people are leaving the system, getting out of the system. Okay, so the guy who get the ticket, like he will just rush inside the theater and it may go down, but that it could be that process, that the rate at or the rate at which this guy serves the people, it could itself be something stochastic. For example, some guys will be very annoying, may ask the receptionist, the ticket guy, a lot of questions and keep him engaged, so that guy will take more time to get served, or some guys just want to grab the ticket and go, so that guy may take less time. So there itself some stochasticity can happen, and also we are saying that when the people are joining, there itself is a stochasticity, every time guy is going to. Now if you know all, suppose if you know the description of this stochasticity, at any time if you know how many people are there in the system, can you at least give probabilistically how many, what will be the next state of the queue here? For time being, let us say people are entering with probability q in every slot, and every slot a guy gets served and leaves the system with probability q. Okay. So if your system currently at n, there are n guys waiting in the queue in slot n, can you say how many people, what are the possible values for xn plus 1? So what are the possibilities? The next guy, so the new value of this number of people waiting in the queue will increase by 1 if a new guy joins, nobody leaves. It is going to decrease by 1 if nobody joins but one guy leaves. It is going to remain same if either nobody joins or nobody leaves, or one guy joins and one guy leaves, right. So to describe this new number of people that are waiting in the queue, does it matter like starting from the beginning how many people are there till round n, or only the previous one, previous slot is enough there, right. Like if I know what is my status currently, I can describe what is going to happen in the future. In a way, the number of people waiting in the queue is already kind of summary of the system, right? What has happened so far, it is capturing the summary of the system, and that summary is itself enough for me to define the future. I do not really need to know what has all happened till x1, x2 all the way up to xn minus 1, all that is enough is xn. So you see that Markov chain is exactly capturing such kind of system, where my current is already capturing or kind of summarizing all my past, that is enough to describe my future. And in many cases this will arise, for example this queue model and the aircraft example I gave, like just that is a toy example, but many realistic examples can be thought of that follow such kind of scenario.
How many people are in the queue
Yeah.
for Markov chain?
Yeah, in that case if I am going to think of this xn as a process, xn process, then this is going to follow.
And what will the service time?
So right now rather than seeing whether it satisfies the Markov property, what I want you to understand here is the motivation. In this example, is it enough for me to know the current state of the system to know the future, or is it like I need to know entire thing that has happened so far to know the future? That is enough, right? In a sense the current state is kind of capturing the summary, that is enough to describe my future. So that is where we want to start using this Markov chains.
But for this we need to know P and Q, which is like impossible to find. Like it is not necessarily true.
Yeah,
It can be variable, no, it can change.
it can change, but see this is what, like I am not saying you without knowing P and Q, you give me P and Q and then I am going to, as an analyst, I am not, so there are parameters, so there are two things, there are parameters, given these parameters as an analyst you are sitting and analyzing and telling what happens. Who is going to give these parameters is a different question. So for example, let's say if you are a planner, you want to plan something, somebody will say I have 10 manpower to do this, somebody says I have this much budget to do this, and somebody will say I have only this much time to do this. So this has been given to you and now you will be coming up with a plan or analysis, exactly like that. So here this description is given to you and now you are analyzing. What is that if somebody is going to say okay the time I have is less, and somebody say okay money I have is less, and somebody say I have less manpower, then you are going to reanalyze with this new parameter and say okay this is the performance. Right now I am just saying like a big boss, okay you tell me what is all happening, what all the things you have, and then I am going to plan and or analyze what is going to happen. Okay. So fine. Okay. Now the way we have defined Markov property, it says that if I tell you okay this at this index I know the status of the system, then from that point onwards I will to explain my system I do not need to know anything about my past. But most of the time it so happens that this time index that we are going to deal with may not be deterministic, itself could be a random thing. Okay, for example, I want to see how much my aircraft goes further when its fuel tanks become half. Okay. So now the point where the fuel tanks become half itself could be a random thing, right, because the fuel consumption that is going to happen, it depends on so much of environment that you are going to face that you may not have control, that itself is a stochastic thing. So your fuel tank may get half in just 2 hours or 1 hour 50 minutes or maybe 1 hour 55 minutes, whatever it could be a random time, and from that point onwards you want to understand. You want to understand how the things behave in the future. So there, this n here could itself be a random quantity, right? So for example, you want to understand, so let us say you just randomly dropped into some cinema hall and at random you dropped in. It is not necessary that when the counter opened, you may have, after that you may enter the queue after 10 minutes or 1 hour or whatever. So the time when you are joining the queue itself could be a random time. Now you want to see, okay, once I join this, how the things, what are the things I am going to say, like what is going to happen. For example, in this case, let us say you may want to analyze, if I join the system at some point, how much time I need to wait before I get my ticket, okay. So to analyze how much time I need to get a ticket, you want to understand, okay, what if my entry time is not exactly deterministic, but that itself is a random, right. So all of us like go and join queue at some in rush, and at some point we join, and from that point we want to analyze. Yeah. This is an arbitrary time, but this is still a deterministic. This is all index, right? This n I said, this is some n. And now I could make it random by saying that, okay, this is xt. T is a random variable. Now T is going to decide which index I will be looking at, okay. So repeat kilo, just this example you can imagine. You are joining this queue, and the amount of time that you need to wait in this queue before you get a ticket, that is a random thing, right, because it depends on how many people were before you, and also depends on the people before you, how fast they are getting served, how much time they are getting served. Now if you know that you have exactly entered at a particular time, you know this, but you may not know, you may be entering this system at random point. From that random point, now you want to analyze, you want to understand how much time I may need to get served, okay. So I am saying a priori, if you know exactly at what time you have entered, it is fine, but if you do not know this time of joining, that itself could be a random, how that is going to affect your future. So now the question is, the Markov property we have discussed so far, does it carry over to the case when I have such a random times? So I want to basically analyze, suppose let us say T is a random number, T is a random variable which is integer valued. Now I want to know maybe let us take it one. So now I want to know, instead now see, like I have now put this, I want to ask you, if I tell you the observation of the states of the system till this random time t, now the next state it is going to take in the state J1 it is going to take in the next round. Can I write it as simply, this is one step, right, Pi J1. So if this T is some fixed n, this is what our description, right, Pij. So this guy is independent of everything else except this xn goes to I, and that is the definition of Pij1. But now I want to ask the question, what happens if this time is not deterministic, is random. So notice that when I make it random, this T could be taking any possible values that this random variable can take. Okay. So now let us make this notation a bit more clear. What I mean by xt, how to interpret this term xt. Okay. So I know that what is xn of omega, the value taken by my n xnth random variable at sample point omega. Now what is x of t means? Value taken by random variable at index t. So this t here we are going to denote it as x of t of omega. So t itself is a random variable. So on that sample point, just first tell me what is the index, and from that index what is the value taken by this xt of omega on that sample omega. Yeah, they will be same. So when I write x of t, the way you have to read it is, so this is a random variable, right, xt. So this is again, so t is from omega to 0, 1, 2 all the way, and I know that x of n is also from omega to r. This is for all n. All my xn's are defined on the same sample space, right. Now when I say x of t, it is just that I am not specifying you which index n, I am just specifying you a random index. So when I write, so this is basically xt of omega, when I write this means first look at the index at the sample point omega and look at its value at this omega. Okay. So okay, another example. Okay, so just let us say if this fits well here. So let us say that I am interested in 100 stocks, okay, or whatever number you take in the stock market, and what I am interested in is how the values of the stocks change on every day. Okay. So let us call these stocks 1, 2 up to 100. I can think of this as in my sample space. Omega is this stocks. Now on each day I can focus on this stock and then see how its value is going to change. If you are going to fix a stock, let us say that corresponds to omega, then you know the value it is going to take on different days. That is one sample path you have. Now what I want is, I would say that okay, the value of my particular stock when its value becomes less than certain number, on the day when its value goes below certain number, let us say. So now what is T is going to be? T is going to describe you that day. How? You have said that particular stock when its value become smaller than some number, right. So that its value may become smaller than some number in some day, you do not know, that could be a random quantity, right. You go to that day and then look at the value taken by that stock on that day T of omega. So, the value that stock has. So, in this case this T of omega basically gave me the day on which the value of that stock omega went below certain number, and then this is going to tell exactly what is the value of that stock. So, you realize that why this random, I may be interested in knowing my value process value at a random time, because you may want to put some conditions like that. For example, you may want to in the stock case you may say that, okay, what is the value of my stock when it is exceeded 500 rupees. Okay. So, you will look for the time when it exceeded 500 rupees, 500, what I am just saying is it is exceeded 500, but its value itself need not be 500, right, it may be 600, but what I was interested in, when it exceeded 500, it may have exceeded 500 rupees on the 100th day, but when it exceeded, what is the price, that will be given by this, and when it exceeded 500, that day is given by this T of omega. So, and here omega corresponds to that particular stock that I would be interested in. X will go from no x, it is not like x exactly. So, x as actually basically I can think of x as index by and with index and sample. So, this same thing we have written as x and omega. So, you understand the meaning of this random variables here. For every n, I am defining x n taking value on omega, I mean assigning values to omega, right, in on real line. So, instead of fixing n, I can just make it a joint one. So, I can think it as so, okay, so I think this, yeah, n belongs to capital N, n is the set of natural numbers, okay. So, either, so you first, so to define a random variable, the process what I asked, give me an index and then give me a sample, then I will tell you what is the corresponding value. So, here I am, instead of separately defining for each index, then I can just say, okay, give me the sample point and give me the index, I will tell you what is the value that it takes. So, in this case this x is a process, we have discussed this, right, when we are talking about a stochastic process. Stochastic process can be thought of as a collection of indices, sorry, collection of random variables where every index corresponds to a random variable, or alternatively we can also think it as random process x as a map which gives value r for a pair omega and n. So, same thing, in that case we can think this as if this n, so here this can be thought of as for, so if x of omega in this case can be thought of as x of t omega and omega. So, sorry, yeah, x of t as, this will going to tell you what is the index we will be looking at and what is the value. So, for example, when I say stock, right, so the t is defining, so on a particular stock omega, let us say you have defined when it exceeds value 500. So, t of omega will tell you that time when it exceeds 500, that index. So, that is fine, I mean that ambiguity is there for time being. For our example, let us assume, or maybe we can refine it as the first time when it takes value 500, we can do all such refinements, then it is going to be unique in that case, and then we can define like this.